Welcome back to your Algebra 1 video series. This is our third lesson for this year. This is lesson 1.3, solving equations with variables on both sides. Really means on both sides of the equal sign. I really just ran out of room at the top. So as a reminder, we're in the middle of your topic 1, which is solving equations and inequalities. We haven't gotten to any inequalities yet. We're really just working on your equations skills. What we're going to do today is build on what we've learned from the last 2 days and get closer and closer to being able to solve every type of linear equation. And again, we'll discuss what linear equations are a little ways down the road. For now, they are all the equations that we're solving. So let's take a look at our opener. You're supposed to look at 3 methods below that have an incorrect step in solving the same equation. You need to identify the error and explain why you cannot use that method. And then if you have time, we should probably solve the equation correctly. Okay, so let's see what they did here. This first one, we had this 3 attached to x minus 5 by multiplication, and it's equal to 12. And it looks like they tried to undo subtracting 5 with adding 5. I think I found our mistake here. Now, we cannot do anything to the inside of parentheses until we've dropped those parentheses. I think always they like to think of parentheses as like a force field, right? We can't get into anything inside the force field as long as the force field is still standing. And so far, the only way we have to drop parentheses is with distributive property. So, in order to do anything to the inside of the parentheses, we have to distribute first. Otherwise, we are not allowed to cancel and go here. So, their mistake is this step right here. That is not allowed. Let's look at the next one. Ooh, the next one is clever. They realized, I think, their mistake from the first one and said, okay, well, we know we have to get into the parentheses at some point to isolate x, so let's get rid of the 3 that's out front. And they said, this is a positive 3, so let's do a minus 3, because a negative 3 and positive 3 cancels, doesn't it? And then they end up here. Oh, but they're making a mistake here, because it's not about just canceling the number. It's about undoing how the number is attached to x. And this 3 up here is attached to x after you distribute with multiplication. Multiplication cannot be undone with subtraction. So the step here where they tried to undo the 3 with subtracting is a no-go, and that is their mistake. Last but not least, let's take a peek here. Looks like they distributed 3 to each term, which is very good. 3 times x is 3x, 3 times 5 is 15. Don't forget the negative. Then they said, oh, let's undo the 3 that's attached to x. And to undo the 3, they multiplied by 1/3. We saw on the first day in lesson 1.1 that if this is 3 over 1, you can multiply by 1 over 3, and reciprocals always cancel each other out. And a third of 12 is really just like dividing by 3. A third of 12 is 4. And then it looks like they added 15 to both sides to get to 19. Well, where did they go wrong? Oh, well, I think they went wrong because whenever you do something to both sides, and this is why I really like the horizontal method, you can't just group part of one side in parentheses. Their mistake is actually this parenthesis, the singular parentheses right here. What they needed to do when they put the 1/3 is they needed to do parentheses around this entire side. So then when they do the 1/3, they can distribute it to the 3x, which is x. But then they also need to distribute the 1/3 to 15, which would turn this into 5. And so that is their mistake. Now, someone might have said, well, wait, they used multiplication, and if we're thinking SADMEP, shouldn't we always undo addition and subtraction first? Shouldn't they just have undone this minus 15 first? Are they even allowed to go out of order? And the answer is yes, you can go out of order. You can undo multiplication and division first. So you could do this. But this order exists because it's the most efficient order to solve. It's actually going to be an extra step if you undo the multiplication first. Sometimes. In this case, maybe not. But I would heavily suggest that you undo addition and subtraction, then multiplication and division. They did ask us to solve this problem correctly, so I'm actually even going to do it in a different way that I think I have the most space right here. So let's take a look at how I'm actually going to solve this. 3 times x minus 5 equals 12. Well, I could distribute here, but another way that I could do this is I could actually divide both sides by 3. That's going to undo the multiplying by 3 and leave us with x minus 5 equals 4. Last but not least, add your 5 to each side, and that will give us x equal to 9, which is the correct answer. So notice I again went out of order here. I didn't do distributive property first. And that's because I realized if I was able to remove the 3, then x would just have a 1 in front, which is way nicer than if x has any other number. So I just removed that by dividing, and bam, we're good. Okay, so we're going to really jump right into our practice today. So let's discuss what it means to solve an equation with variables on both sides. Well, I'm actually going to take a quick peek at an example, and then we're going to go back to the previous page. So far, we've only solved equations that had x either on the left side of the equal sign, or it had x on the right. But today, we're going to have equations that have x's on the left and the right. And if we're going to want to solve this type of equation, somehow we need to bring all the x's to one side together, because eventually our answer has to say x equals something, right? X is all on the left. Or it could say something equals x and all the x's are on the right. Having them on two separate sides isn't going to be super useful. Well, how do we deal with that? Okay. Very, very similar to last class. Last class we discussed at the very beginning, before you start doing things to both sides, you use what we call properties of expressions to simplify each side of the equation individually. Those properties were distributive property and combining like terms. So we're still going to do the same thing as last class. It's a great way in terms of solving equations to simplify so that you have less work to do. Now, step 2 is the only thing we're going to add a little bit to. If you have variables on each side of the equal sign, I really suggest that you add or subtract, right? This is still going to take us through SAD/MEP. I suggest you add or subtract the variables until they're combined on one side of the equation, right? Don't forget, SAD/MEP tells us to add and subtract, and this is the new part for today, as many times as necessary until all the addition and subtraction is gone. We've been used to two-step equations where we only had to add or subtract once and then multiply or divide once. That's it. Today we're going to add or subtract more than once, probably. We're going to do it a few times. Once there are no more terms to add or subtract, then and only then are we going to move on to the D and M, the divide and multiply step. Now what we're going to do on the next page is actually try each problem solving it in a different way. So let's rock and roll. 1A, 1B. Notice that 1A and 1B are the exact same problem, so let's take a look. First thing we try and do is simplify. I don't see any parentheses, so we're good there. And this is the tricky part that I see people make mistakes on. There are no like terms on each side of the equal sign. If you look just on the left side, we cannot combine 4x and minus 2. If you look just on the right side, you cannot combine 6x and 10. So there are no like terms to combine on each side separately. And so now we get to move into SAD/MEP. So we're going to start with just addition and subtraction. I really like, that's personal preference, to move the x's to one side first. When we move the x's to one side first, and I'm going to rewrite this just so it's a little bit larger here, it doesn't matter where you start. We need to realize, though, that technically we are adding 4x and subtracting 2 on the left side, and we are adding 6x and adding 10 on the right side. There is a lot of addition and subtraction here. Addition, subtraction, addition, addition. We are going to undo that addition by adding or subtracting. And so to really highlight this, I'm going to undo the adding 4x first. To do that, we subtract all of this off, the 4 and the x together, right? We're not just subtracting 4, those wouldn't be like terms. We're subtracting all of this together from each side. And notice that I lined the 4x's up with their like terms. I didn't do it to the minus 2. I didn't do it to the plus 10. Just their like terms here. 4x minus 4x is 0. There's nothing left there at all. No x is nothing. We're left with negative 2 equals 6 of something minus 4 of something is 2x plus 10. Once you've moved all the x's to one side of the equation, notice all the x's are on the right side now, then it's just a two-step equation. There are two numbers attached to x, 2 is multiplying, 10 is adding. What do we undo first? Oh, well, we undo adding 10 first by subtracting 10, like so. Negative 2 minus 10 is negative 12. 2 is still attached to x by multiplication, so we should probably divide that 2 off. Notice I just divide by 2 here, not 2x. If you divided by 2x, everything would cancel, just the number in front of x. Anything divided by itself is 1, but we don't need to write the 1 in front of the x. Negative 12 divided by positive 2 is negative 6. The end. Now, I showed the vertical method going up and down to add and subtract to both sides here. On 1b, I'm going to show the horizontal method, the side-to-side method, just so we can see the differences and similarities. And the other thing to notice is I had to add or subtract twice on this problem, but I still only had to multiply or divide once. And that's going to be pretty common. You should only have to multiply or divide one time, but you might have to add or subtract more than once. So let's try 1b. Same problem, of course, so I'll rewrite this. 4x, I'm going to leave a little gap though, minus 2 equals 6x plus 10. Now we really have four options here. I could subtract 4x from both sides like I did over here. I could add 2 to both sides. I could subtract 6x from both sides or subtract 10. We do the inverse operation of any one of them and they're all correct steps. I really like, though, to always start with the terms that have x's so that all of your x's are on the same side. So, because last time I subtracted 4x, I canceled out the 4. This time, let's cancel out this positive 6x. To do that with the horizontal method, we group both sides and we subtract 6x. Now remember, with parentheses, we discussed this on the previous page, technically we can't do anything to the inside here to the 6x and 10 until we drop the parentheses. We only drop parentheses with distributive property, so what number is distributing? Well, it's not the minus 6x because we don't distribute subtraction or addition. In fact, it's the invisible 1 that's out front. But if you distribute an invisible 1, does anything change? No, I don't think so. So really we have 4x minus 2 minus 6x equals 6x plus 10 minus 6x. And then we combine like terms. 4x minus 6x, that's going to give us, of course, negative 2x minus 2 equals, and then on this side, a little bit harder to see, we have 6x minus 6x. Anything minus itself is 0. I should probably do it like this, so we see that it's gone, and that leaves us with 10. Now, could you have gone from here to here? Of course you could. I just showed that intermediate step, that middle step, just to demonstrate what's happening with the parentheses. What do we have left? Oh, it's a two-step equation. We have the negative 2 that's multiplying and the 2 that's subtracting. So let's undo subtracting 2 first. Apparently I'm moving back to the vertical method, which is silly because I don't have enough room here. So I'm going to do it like this. We're going to add 2, and then I'm going to be clever over here, and I'm going to do 2 plus. There we go. Now I have enough room. The 2's will cancel. They make 0. That leaves me with negative 2 times x equals 10 plus 2, which is 12. Last but not least, we should probably divide off the negative 2, like so. These undo, they make a 1, and that gives us x equals negative 6. Is that the same answer? Ooh, it is. Notice the x is on the left side instead of the right this time, but it is still the same answer. Now that you get the idea, please go ahead and try problem 2 and problem 3, but please try these doing at least one different step each time. So make sure 2a and 2b you don't have the same process, and the same for 3a, 3b. Once you've done those, unpause the video, because you should pause it right now, because you should work on your own. Unpause the video, look back over my solutions, and make sure you did it correctly. Even if you solved yours differently than I did, you should still get the same answer. So let's take a look. For the second one, I'm going to be a little bit more traditional, though I am going to do a few steps at the same time. We learned last class that if you have a 2 minus, you don't distribute the 2. Instead, you remember there's a negative 1 attached that needs to distribute. So that's going to give us 2 minus 1x minus 3, negative times a positive. On the right side, I see a negative 7x, which will combine with 10x. I'd rather think of that as 10 minus 7, which is 3x's, and then 5 minus 4, which is positive 1. Okay, from here, you might notice that this left side, we still need to clean up a little bit because we have like terms here as well. We have a 2 minus 3, which is a negative 1. I like to put the x's first, though, so I'm going to do a negative 1x, and then I'll put the minus 1. Nothing to do on the right side yet. From here, I mentioned that I always like to move the x's first, right? So when I move the x's, I have two options. I can either add 1x to each side, or I can subtract 3x from each side. And it's totally up to you. However, you might notice if you subtract 3x here, that your x's are going to stay negative, and just personal preference, I always like my x's to be positive. It's totally up to you, but I'm going to go ahead and decide to add 1x to each side. That will, of course, zero out the x's here, leaves us with negative 1 equals 4x's plus 1. Once all of your x's are to a single side, now it just becomes a matter of SADMAP. And we already did some addition and subtraction, but now it's even more. We have a 4 that's multiplying times x and a 1 that's adding. We should know we undo addition and subtraction first, always working with the side that has x. These zero out. Negative 1 minus 1 more is negative 2, which is equal to 4 times x. Finishing this off, we need to divide by 4. That makes 1. Negative 2 divided by 4. Well, I don't think 4 goes nicely into 2, so technically you could stop here. However, that's kind of a weird answer, and it's weird because this is a fraction that we can reduce. I think we can divide both the numerator and denominator by 2. The negative stays, and we get negative 1/2. That's probably our better answer, our more accepted answer. Now, of course, you could also write the decimal. Any one of these is okay. Pick your favorite, but there's that. All right, I said we can do this in different ways, and we certainly can. For example, one thing that we could do at the very beginning is this pesky positive 2 that's out front. I could subtract that 2 here. Now, sometimes this gets a little bit weird because people are like, wait, you're subtracting on one side, I do it on the other, but there's a 5 and a 4. Do I subtract everywhere there's a like term? And the answer is no. You always do something only once on each side. So I'm going to rewrite this to show you. I'm going to put this in parentheses, 2 minus x plus 3, and I'm going to undo the positive 2 by subtracting 2 at the end, that horizontal method. And then I'll do the same thing over here. Negative 7x plus 5 plus 10x minus 4. We always undo something by doing it just once on each side. Now we learned that outside these parentheses there's a 1, so we can really just drop them and combine your like terms right away. That's going to give me negative x plus 3 equals, and then on this side, let's just combine a whole bunch of like terms at once. We might as well. We have this negative 7x plus 10x. We already know that's 3x. We did that before. But then we have 5 minus 4, which is 1, minus 2 more, which is negative 1. All right. Now, let's distribute. And you could think of just distributing this negative. Technically, it's a negative 1, but if you just multiply a negative in, it just does the opposite of the signs inside. It becomes negative x minus 3 equals 3x minus 1. Okay. And then some people are like, well, wait, what if you don't move the x's first? Can you move the numbers that aren't x's first? Sure you can. There's nothing wrong with that. In fact, I could be really weird, and I could move everything on the right side to the left side. Sometimes people do that. So, for example, I could go ahead and add 1 to cancel out this 1 to each side. If I do that, combining my like terms, these will zero out. That leaves me with 3x. 1 minus 3 is negative 2 and negative x. What if I even wanted to add or subtract this 3x to the other side? Could I do that? Sure, we have to move the x's at some point, so let's go ahead and subtract 3x, not divide by 3. I'm going to subtract 3x. And by the way, if you subtract 3x over here, it's kind of weird if you don't do it at the end. We have to show minus 3x that is adding to the parentheses. That's very, very strange, and maybe you can think about why. Right, if you move this out front, you can see it's a minus 3x. Okay, so when we combine like terms, let's try this. On the left side, we have negative 3x's minus 1 more x. I think that's going to give us negative 4x's, and then there's still the minus 2. On the right side, though, I have 3x minus 3x. Anything minus itself is 0. So do I have to write anything? Well, yeah, we probably should here because we want to fill up that blank spot. So equals 0. All right, now what? Well, everything's on the left side, but all the x's are on the left side, which is good. There's two numbers attached to x. Negative 4 is multiplying. 2 is subtracting. So let's undo subtracting 2 from both sides by adding 2. Okay. These ones cancel. That leaves us with negative 4x equals 2. And we know we undo multiplication by division. Divide both sides by negative 4. That makes a 1. And it gives us our answer of x equals that same fraction, 2 divided by negative 4. Now, some of you really astute students who are paying super close attention, might realize that the negative on this fraction is on the bottom and this one that's on the top. Does it matter? And the answer is no. You actually have 3 places you can put a negative in a fraction: the denominator, the numerator, or, I'm going to simplify this to 1/2, right in the middle. And they all pretty much mean the same thing. It's more common to put it in the middle, but if you want to move it on the denominator or numerator, you totally can. Notice we got the same thing, but did it pretty differently this time. I'd say 2a is probably more efficient than 2b, but it still works. All right, let's look at this guy. Oof, decimals. All right, here we go. It's 27x right there. All right, so first step, I'll just be traditional. I'm going to go ahead and distribute the 0.2. We'll deal with decimals. We don't do it too often, but it's not a bad thing to do. 0.2 times x is 0.2x. 0.2 times negative 4. 4 of those 0.2s, 0.2, 0.4, 0.6, 0.8, negative 0.8. On the right side, negative 16.8 plus 27x. Now, I'm noticing something in particular. My next step is going to be to combine like terms, right? We always distribute and combine like terms. I'm noticing that when I combine 34.8 of these x's plus 0.2 more, that actually makes a really nice whole number, an integer. 34.8 plus 0.2 is 35 x's. And so I have a sneaking suspicion that even though this problem looks like it has decimals, maybe it actually will all come out super nicely. So what am I going to do next? Well, so now I have x's on the left, x's on the right, nothing to combine like terms for. I really like to move all my x's to one side, and I like to keep them positive. So this 27x that's on the right and the 35x we'll have to bring to the same side. We do that using SADMAP, and we always undo addition and subtraction. I'm going to subtract the 27x because I know that 35 minus 27 will be a positive number. In this case, I think it will end up being positive 8x minus 0.8 equals negative 16.8. Okay, now we have all the numbers, or we have all the x's on the left side, so we just undo what's attached to x. 8 is multiplying, 0.8 is subtracting. We undo the subtraction with addition. Decimals and integers can be pretty darn tricky. Negative 16.8 is moving 0.8 more positive, so I think those are actually going to cancel out and leave us with just negative 16. And now we have a pretty nice problem. 8x equals negative 16, right? Divide both sides by 8. 16 divided by 8 is 2. Negative by a positive is a negative, and we're set. All right, are there other ways to do this? Sure, probably. Let's use the trick that we learned last class, the trick where we can get rid of these decimals. So my very first step here is I'm going to take all of this, 34.8x plus 0.2, and I'm going to multiply all of this, I'll do it in a different color, all of this times 10. Why times 10? Well, we learned last class that that's going to cause each decimal to move over. Of course, I should do that to the other side too. And we'll do negative 16.8 plus 27x, and also times 10. Decimal moves. Oh, this decimal's already here. It moves one more. It's going to be 270, so keep that in mind. Now, remember, this 10 has to distribute, and it distributes to the first term and to this whole second term, but it's not going to do anything to the numbers in parentheses. It's only going to distribute to the guy on the outside. Remember, parentheses are kind of like a force field. Just deal with the coefficient. All right, so what do we have? This looks like 348x plus 2 times x minus 4 equals negative 168 plus no longer 27, but 270x. Well, on the plus side, no more decimals. We should probably distribute this too, though, huh? 348x plus 2x minus 8 equals negative 168 plus 270x. Can we combine like terms? Sure. 348x plus 2x gives us 350x minus 8 equals negative 168 plus 270x. Now, I'm going to be a bit of a rebel here, and realizing that there are 4 terms left and we do have to move all the x's to one side, we also might realize that if all the x's move to the left side, then don't all the non-x's have to move to the right? So I'm going to be super advanced and do 2 steps at one. I know that I'm going to subtract 270x so that it joins the 350x on the left side. But I'm also going to add 8 to each side so that I move all my 1's over to the right side. 2 steps in one. There's nothing wrong with that, and I'm showing both steps too. So what zeroes out? The 8's are going to zero out, and the 270's will zero out. This leaves me then 350 minus 270. I think we saw that before. That's 8, but 80x equals the negative 168 plus 8 is negative 160. Pretty good. Only 1 step left. Divide off the 80. How many times does 80 go into 160? Well, twice, and a positive divided by a negative. All right, so that's that. Nothing too terrible here. Just some nice practice problems. I'm going to box my answers over here. Makes me happy. And I think we have the idea. So again, we really only added in one new step. And that new step is how to deal with x's on each side of the equation. And the way we deal with it is always with addition and subtraction. We add or subtract the x's to bring them to the same side. Once you get down to a 2-step equation, then it's back to the basics for you. This is really the end of the main part of this lesson. And in fact, at the very end, there's some practice problems for you. However, I'm not going to do these practice problems. There's a riddle, and the nice part with riddles is you'll know if you did it right if it matches one of the answers down here. If it doesn't match one of the answers, you did it wrong. To conclude class today, though, we just have a really quick discussion about equations with no solution, infinitely many solutions, and 0. Okay, so let's go ahead and look at each of these equations down below. Now, I'm actually not going to solve most of them. So I'm going to start solving the first one, though. It says 2x plus 4 equals 2 times x plus 2. If I distribute my 2, like I would when I'm starting to solve, I'd get 2x plus 4 equals 2x plus 4. And the question we'd ask then is, okay, we ultimately want to get x alone. But why are we solving for x? What is the point in solving for x? Well, the point in solving for x is you're looking for the value that when you substitute this value back in for the x's, the left side equals the right. That's how we started our very first lesson. I gave you answers and said, substitute them in and tell me if the left side equals the right. But what might you notice about the left side and the right side here when we've done some simplification? Do you notice that they're the same? And if they're the same, then what number is going to make the left side equal to the right? Let's try a couple. Let's try like x equals 1. Let's see if that works. That'll be 2 times 1 plus 4, and we want to make sure, I'll put a question mark above, is that equal to 2 times 1 plus 4? Well, 2 times 1 is 2, and 2 plus 4 is 6. 2 times 1 is 2, 2 plus 4 is 6. And no, that was not me repeating. Or maybe it was me repeating, because they're exactly the same, aren't they? So 6 equals 6. That means that x equals 1 is a solution. But are there more solutions? What about x equals negative 2? Well, that would be 2 times negative 2 plus 4. Is that going to be equal to 2 times negative 2 plus 4? Well, this is negative 4 plus 4, which is 0. negative 4 plus 4, which is 0, that does work. And so x equals negative 2 is a solution. In fact, you might realize this is kind of a silly experiment because 2x plus 4 equals 2x plus 4 is identical. If the left side is equal to the right, this is actually known as an identity. And if they are identical, how many solutions are there? Well, there are an infinite number of solutions. So there's a few ways to do that. You could say infinitely many solutions. But sometimes people will even say something like all real numbers. Because you might remember that real numbers are any number that you can think of. Fractions, decimals, negatives, positives, pi, anything like that. Any number that you substitute into each side will make them equal. And so sometimes you hear someone say the answer is all real numbers. In fact, if you get really fancy, sometimes they'll even write what we call a double bar R, where it's an R that has two of those bars as its base, and then you complete the R. That is the symbol for real numbers. And so sometimes you might even see that for someone to tell you, oh, the answer is all real numbers. Well, what about this next one? 2x plus 4 equals 2x plus 3. Well, I think pretty clearly the left side is not equal to the right side. They are not identical. So let's maybe just look at a couple answers and see if we can determine what's going on here. I'll just try 1 and 2. So if I tried x equals 1, that would be 2 times 1 plus 4, and that would need to be equal to 2 times 1 plus 3. Well, 2 times 1 plus 4 is 6, 2 times 1 plus 3 is 5, and 6 is certainly not equal to 5. So 1 wasn't the solution. Let's try another. X equals 2. That becomes 2 times 2 plus 4, and we need to see if that is equal to 2 times 2 plus 3. Well, 2 times 2 is 4, 4 plus 4 is 8. 2 times 2 is 4, 4 plus 3 is 7. 8's not equal to 7. But you might start to notice a pattern about the left side versus the right. In fact, I think the answer on the left side is always one larger than the answer on the right side, isn't it? Well, is that always going to be the case? I think so, because this 2x and this 2x are in common. But then after we do 2x, we add 4. And here after we add 2x, or we do 2x, we add 3. So it seems to me like the left side will always be 1 greater than the right side. And if that's always true, then what number will make the left side equal to the right? And this answer is, of course, no solution. There is no value for x that will cause the left side to equal the right. Okay, let's take a look at one more. 2x plus 4 equals 3x plus 4. Well, they have the 4's in common here. I think, honestly, let's just go ahead and solve this guy. I don't see anything that's too similar. So remember to solve, x is on two different sides. I always like to bring my x's to the same side using addition and subtraction, and I like the x's to stay positive. So this 3 is bigger than the 2. I'm going to subtract 2x from each side. Okay. So leaves us with 4 equals 1x plus 4. I think we could probably subtract the 4 off here. And let's see what happens. I don't even think I need the 1 in front of x. That's just x, isn't it? And then 4 minus 4 normally does 0 out, but we do need the 0 to fill the place on the left side. And I think we're actually done. We get x equals 0. So does that mean no solution then? Well, let's check that really quickly. I think 0 is a number, right? It lives between -1 and +1 on the number line. So let's try x equals 0 and make sure that actually works as a solution. So it would be 2 times 0, I'm using the equation at the top, plus 4 equals 3 times 0 plus 4. Well, this becomes 0 plus 4 equals 0 plus 4. And that is indeed true. 4 does equal 4. X equals 0. Wow. Okay. Well, as a reminder, please don't be mean to the number 0. Sometimes students do get an equation that thinks x equals 0. Oh, that means no solution. That's not true. 0 is a number. There are situations where you get no solution or infinitely many solutions, but 0 is not one of them. Now, some conclusions here. Linear equations, all the equations we've been solving so far, can have no solution. They can have one solution, like x equals 0 is a single solution, x equals 12 is a solution, or infinitely many solutions. For an equation to have no solution, there is going to be no value for x, which makes the equation true. So what does that mean? It means the left side never equals the right. Now, sometimes you don't actually see that ahead of time, right? You might have looked at this problem, you might have been in the zone and said, I'm just going to solve it, I'm going to solve it. And that's okay, because something special happens when you solve an equation with no solution. So this equation, and I'm actually going to do this twice, guys. I'm going to show you some different ways students do this. So 2x plus 3, I think it was 2x plus 4 first. Sure. 2x plus 4 equals 2x plus 3. Well, the most direct way to solve this is to move the x's first. So I'm going to go ahead and subtract 2x to each side to bring all my x's to the same side. 2x minus 2x is 0, 2x minus 2x is 0. We don't need to write those because there are still numbers on the left and the right. 4 equals 3. Okay, now to isolate x. Oh wait, there aren't any x's left. So what's going to happen with this no solution situation is all of your x's, if you do SADMAP correctly, will cancel out. And you're going to be left with this 4 equals 3. 4 is not equal to 3. You're going to be left with a false statement. And if you get that, that always means no solution. Now, sometimes students do things in different orders, which is totally okay. You never have to follow Mr. Grant's prescribed method for solving an equation. So sometimes students will say, I want to move the 4 and the 3 first. Okay, there's nothing wrong with that. You can subtract 4 from each side. Okay, and they get 2x equals 2x plus, no, minus 1. And then they say, all right, well, now I want to add 1 to each side. Okay, you can do that too. When you add 1 over here, though, notice that 1 and 2x are not like terms, so they just have to sit next to each other. And then they get a little frustrated. They're like, okay, now I'm just kind of going back and forth. Eventually, though, they'll probably realize that they should subtract 2x from each side. And if we do that, we are left with 1 on the left side, and 2x minus 2x, we do need to write the 0 to be the placeholder on the right side. 1 equals 0. That is still a false statement. So no matter how you play around with the equation, here I got 4 equals 3, here I got 1 equals 0, we still get something false. And notice that the left side is still 1 greater than the right side. Just what we found up above, our answer on the left was always 1 greater than the right. An equation with no solution will eventually cancel all the terms with x and end with a number sentence that is false. Give 2 examples. Well, I just gave some examples up there, but we can do more. 10 is not equal to 7. 0 is not equal to 100. If you get anything like that, no solution. All right, last but not least. Equations with infinitely many solutions do not always mean that every number works in the equation. Right? For example, you might solve an equation where only even numbers work, only 2, 4, 6, 8, 12, 10, 12, so on and so forth. That's infinitely many solutions, but it's not every number, right? 1, 3, 5 don't work. It's an infinite number of solutions, but it's not always every number. However, the nice part is for this semester, at least, when we get infinitely many solutions, it will mean every number. All right, let's go ahead and fully solve equation A. Then as a reminder, I'm going to do this twice. Equation A was 2x plus 4 equals 2x plus 4. The most efficient way to do this is to subtract 2x from each side. Here and here. And that leaves us with 4 equals 4. That is true. But what if you decide to surprise me and work a different way? And you're like, instead of subtracting the 2x's first, I want to get rid of the 4's. Okay, you can do that. Subtract 4, 0, 0. 2x equals 2x. Now at this point, I've seen many students do this in the past. They go, ooh, x is by itself. I'm going to divide now. And you can do that. You can divide by 2. But remember, we're not dividing by 2x, just by 2. So what's going to happen is we get these 1s. The x's are still there on each side. X equals x. Can you go further? Sure. You could subtract x from each side. Adding and subtracting makes zeros. But we can't just leave it blank, so we do need to put in the zeros. Eventually, no matter how you solve an infinitely many solutions equation, you should get a number sentence that is true. As mentioned, these are known as identities. If you want 2 examples of equations that are identities, you could do something easy. 3x minus 1 equals 3x minus 1. Those are identities. They're identically the same on each side. Sometimes the equation will be a little harder, like 2 times x minus 3 equals 2x minus 6. Those are identical as well if you distribute. But no matter what, when you solve these, you will get a true number sentence, a true statement. And these are infinitely many solutions. Thank you for hanging out with me today. If you get the chance, please do the riddle on this back page. Check your answers. If you go wrong anywhere, ask a classmate, ask Mr. Grant. He's happy to tell you if you did everything right. And now you are even that much closer to being a master at solving linear equations.